Exclusive events have no elements in common. I could represent that if this is our sample space and we have event A and event B represented by those circles, that those events are mutually exclusive. We would say that they're disjoint. They have no elements together that are in common. And if we wanted to find the probability of A union B with these mutually exclusive events, that means either A or B, the probability of the union of these mutually exclusive events is the probability of A times the probability of B. Okay, if we have two, let me move these a little bit further out. I'll pull them up in a minute. If we have two events maybe that are not mutually exclusive, let's say this is our sample space, and this time A and B are going to overlap. The area that they share would be the events in common. The red is the events that are in common to both A and B. And so if we wanted to find the events that are in common to both, the probability of A intersect B, that's union, not intersect. A intersect B. In other words, what's common to both? That's going to be equal to the probability of A plus the probability of B minus the probability of their union. And I'm running out of room here.
So what is that?
Hang on. I can't. I moved it. Minus the probability of A union B.
Was it intersect?
Intersect B, sorry.
Pretty sure that's on the.
Okay, the probability of A intersect B is the probability of A plus the probability of B minus the probability of the intersection of the two. That's if we want either A or B, the probability of A or B. And I put the wrong, sorry. That should have been A or B. And did I get the other one backwards? I think I did. No, this is if they're mutually exclusive.
That's PA plus PB?
Yes. So if they're mutually exclusive, we take the probability of A plus the probability of B. If they are not mutually exclusive, we take the probability of A plus the probability of B and subtract out what's common to both.
Can you write the formula?
Yeah, can you rewrite the formula if they have them in common?
Yeah, let me move that out of the way. All right, we'll rewrite it. The probability of A, that's what gets me messed up, is the A. I should have used a different letter probably. The probability of A or B. This is A or B. is equal to the probability of event A plus the probability of event B minus the probability of what's common to both. Minus the probability of A
The same thing.
intersect B.
Is it intersect or, okay.
What is the U?
Intersect, union.
Yeah, isn't the beginning of the formula the same as mutually exclusive?
It is, because if they were mutually exclusive, it's just the probability of A or the probability, plus the probability of B. But now if we want the probability, but they've got some points in common, we have to subtract out the points in common.
How do
Nick?
we find the probability of A intersection B?
Okay, let's look at an example. All right,
No,
Miss Colvin.
yes.
What means that, like, you reverse?
Intersect, where do they intersect? What's
they-
common to both? What's common to both?
And the other, and the U?
Union,
You-
A or B. This one is A and B, common to A and B. All right, so let's look at this example. I think this example, I just took the picture out of your book, but it says that one card is selected from a standard deck of 52 playing cards. What's the probability that the card is either a heart or a face card? Now, here on the picture, you have the hearts. In the pink, you've got the face cards. But notice there's an overlap. You've got face cards that are hearts, so we have to take those out. So if we want to find the probability of, let's say, the probability of a heart. How many hearts are there? 13 out of 52. What's the probability of a face card? Three for each suit. There's how many suits? So there's 12 out of 52. Okay, so we found the probability of hearts, the probability of the face cards. How many are common to both?
There should be 3 face cards that have hearts.
The probability of what's common, change that to H. What's common to both? So used to making an A. How many are common to both? 3. So the probability of either a heart or a face card. 52, yes, thank you, and I probably can't change that now. The probability of either a heart or a face card is going to be 13 50-seconds plus 12 50-seconds minus 3 50-seconds. So we add the two separately and then subtract what's common to both. So that gives us, what, 15 minus 3? Did I add that right?
Well, 352, which is 3.
25 minus 3 is 22. So the probability of a heart or a face card is 11 out of 26.
Where did you get the 3 out of 52?
Let me do this. Quick correction. Probability of A and B.
That means that they have something
The
in common,
probability of A, if these are independent events, times the probability of B. This is for independent events.
So
They would have nothing in common here.
Okay, so mutually exclusive events are things that have.
Mutually exclusive, independent events. What happens the first time has no effect on what happens the second time.
They're the same thing.
All right,
Yeah, okay, they're the same thing.
but we could have mutually exclusive where we take or. Okay, if it's mutually exclusive, and we take the probability of A or B. This is the probability of A plus the probability of B.
So there's three formulas.
And if they're not mutually exclusive, the only difference is you subtract out the intersection.
So these are not mutually exclusive events if it's or.
They could be.
Why is it you now?
It was always.
What is going on?
What happened to the upside down one?
Eventually, we're gonna need to write those.
Here, the personnel department of a company has compiled data on the number of employees who've been with the company for various periods of time. The results are shown in the table. Right, the question says if an employee is chosen at random, what's the probability that he has 4 or fewer years of service? So we want to know the probability that he has 4 or fewer years of service. And we'll just call that event A. How many total employees do we have? Can't spell anymore. How many total employees?
Well, wouldn't, you can't add them all together, right? Because, they're
Why not?
like 8
What's the total sample space?
total sample space.
Total sample space is the total number of employees.
529.
529 employees. How many have 4 or fewer years of service?
157 over 529.
Okay, so that's the probability that you're going to get if you randomly choose that you're going to pick one that's got 4 or fewer years of service. Okay? You could get a decimal if you wanted to, and that would be a percent. If you divided that out on your calculator, you'd get a decimal, which would be then you could change that to a percent. All right, let's think about the B part, that they will have 9 or fewer years of service. What do you think we're going to have to do here?
You'd add all of them together and then subtract 157.
Okay, do they have anything in common?
No. Well, besides the fact that
Yes.
How many have-
89.
Not less than 9 years is 157.
Okay, let's say we want the probability of 5 to 9. I'll just put 5 to 9. What's that going to be?
Probability it's 89 plus probability of B.
89 over 529. All right, so let's think about this. Are they mutually exclusive? We've got 2 groups here.
Well, they both have the same.
Okay, they mutually exclusive. So how do we find? Uh-huh.
9 or fewer. Wouldn't that be 9
Okay.
all the way to 0?
But we're looking at 5 to 9 and then 0 to 4. So within those little subgroups, from 0 to 4 years, from 5 to 9 years, do they have any overlap? No, so they're mutually exclusive. So if we want to find the union of those two, the probability that they have 9 or fewer, So we're going to say the probability, I'll just use A and B, that we have 9 or fewer. That's going to be 157 over 529 plus 89 over 529. And I think that is, what, 246 out of 529?
Yep.
And if we got a percentage, that would be approximately 0.465, or 46.5% have 9 or fewer years of service. The probability is 0.465, but if we could convert that to a percent. Notice there wasn't any overlap. Okay, here, y'all don't have this example in your book. It says a wind turbine plant has a total of 158 wage and salary workers. The circle graph gives the age profile of these workers. What's a probability that a person selected at random from the plant is in the 35 to 44 age group? Can you read those? 35 to 44 is
47%.
right here. Okay, so the probability is 27 out of 100, or 27%. Do you have any overlap between the groups here? So these are mutually exclusive. All right? What's the probability that a person selected at random from the plant is in the 35 to 54 age group? I just did that one. Okay.
47%.
35 to 44. Okay, 35 to 54. How would we find 35 to 54?
27 and 20.
We would have to add those two probabilities together, and it would be 47%. You add those probabilities because they aren't mutually exclusive. 27 plus 20. Does that help a little bit to see the difference between, that lets you see where they're mutually exclusive or not? Okay, we said for an independent events, the probability of A union B, A and B.
You said intersection.
Yes, you're right, intersection. Is the probability of A times the probability of B. And when we're talking independent events, the occurrence of one event has no outcome on the second. So, a random number generator on a computer selects 3 digits or 3 integers from 1 to 20. Okay? Randomly selected. What's the probability that all 3 numbers are less than or equal to 5? Okay, so what's the probability? He's spitting out 3 different numbers from 1 to 20. We want to know the probability that it is less than or equal to 5. So what's the probability that you're going to get a 5? It is less than or equal to 5.
5 out of 20.
5 out of 20. Less than or equal to 5. So the probability that you're going to get a number less than or equal to 5 is 1/4. All right, so there's 3 numbers it's spitting out. It's going to be the probability that the first one is 1/4. The probability that the next one is 5 or less is 1/4. And the probability that the last one is 5 or less is 1/4. So we have 1/4 times 1/4 times 1/4, which is 1/64. Okay? Think about this one. Same random number generator. You're looking at numbers from 1 to 30. It's just going to select two. Two integers from 1 to 30. What's the probability that both are less than 12?
Wait, so does this mean the integers can repeat? Like you can choose the same one twice?
Could, doesn't matter. It's random. I mean, the first one that spits out, it's a number.
So you can choose
Does
like
that have any effect on the second one that's being spit out? No.
But is it
So-
less than or equal to 12?
Just less than 12. What's the probability that both of them are less than 12?
0?
I said 1 to 30.
So
So you got one.
11 over 30
You've got
times 11
got
over 30.
11. You've got
Part, what'd you say?
Say 11 over 30 times 11 over 30.
Okay, the probability that the first one is less than 12 is what? 11 over 30? And the probability that the next one is less than 12 is 11 over 30.
So you've got 121 over 900.
121 over 900. And no, I don't think that'll reduce. Does that make more sense as far as the independent events? Because what happens the second time is the first event had no bearing on what happens the second time.
how did you know that it's independent though?
Because it's a random number generator. Spits out a number. Then it's going to spit out another number. Does the first number that it got have any bearing on the second number that's coming out? So they're independent events. Says a sales rep makes a sale at approximately 1/3 of all his calls. So if he goes to 3 different calls, he'll have usually 1 out of 3. On a given day, he contacts 5 potential clients. What's the probability that a sale will be made with each of the 5? Okay, so what's the probability for the first one?
It's 1 out of 3. Yeah.
1 out of
Second,
3.
third, and fourth, fifth.
And then the second one would be 1 out of 3. And the third one would be 1 out of 3. So is there a short way we could write that?
Factorial 1 out of 3.
Not factorial.
1 out of 3 to the 5th.
1 out of 3 to the 5th.
Whoa.
Because he's got 5 clients he's going to go see. Probability is 1/3 for each client. So 1/3 times 1/3 times 1/3 times 1/3. And so that is
1 over 243.
27.
243.
Yeah.
Yeah, because 3 to the 4th would be 81. Yeah,
Yeah.
1 out of 243. All right. We want to also talk about the complement of an event.
Wait, what was that called?
That was just another example of independent events. Whether he was successful on the second call had no bearing with whether he was successful on the first call. Okay, when we talk about the complement of an event, say the complement of event A is the collection of all outcomes that are in the sample space that are not in A. The complement of event A is the collection of all outcomes in the sample space that are not in A. The complement of A would be represented by A prime. So A and A prime are mutually exclusive.
Wait, collection of outcomes.
That are in the sample space that are not in A.
What's the prime symbol?
That just means it's the complement of A.
Is it A to the first pound?
It's just a little dash.
A.
Like a,
Complete of.
Like a prime, well, y'all don't do that, never mind. I'm thinking calculus, we have a
Oh,
prime.
you got primes in biology.
Okay, so the probability of A plus the probability of its complement are always gonna be 1. Because it's either gonna be in A or in the complement. So for instance, if the probability of winning a game is 1/4, probability of winning a game is 1/4, what's the probability of losing the game? The probability of losing would be 3/4. 1 minus 1/4. If, here we have, a manufacturer has determined that a machine averages 1 faulty unit for every 1,000 it produces. What's the probability that an order of 200 units will have 1 or more faulty units? So we know the probability of a faulty unit is 1 out of 1,000. What's the probability that it won't be faulty?
999 of
999 out of 1,000. Yes, sir.
So the A with the thingy there,
That's
Is-
the complement.
the complement, what's the complement?
I just said what the complement was.
Yes, but I don't understand.
It is the complement of an event is the collection of outcomes that are in the sample space that are not in A. So if you've got a sample space and this is A, the complement is everything else. Everything that's not in A.
Oh, okay. Yeah.
This would be the complement. Everything that's not in A.
So the sample space, no?
It's the elements in the sample space that are not in A.
Okay, thank you.
All right, so if one way that we could answer this is by thinking about what's the probability that you won't have a faulty unit. So you said that the probability of a good unit here, and I'll just use G for a good unit. The probability of a good unit you told me was 999 out of 1,000. And how many units are sold?
200.
So for each one, the probability that it's good is 999 out of 1,000. This is one way we could use the idea of a complement. All right, so what is this? Just 0.81?
0.82.
So what is the probability that it is that one would be faulty? One minus 0.82, which is approximately 18.18 or 18%. Just one example of how you might use that. Probably the most likely that you'd see is like the example that we talked about a minute ago. If the probability that you win a game is 1/4, what's the probability you don't? You just subtract from 1. It's one of those things that just makes sense if you think about it.
How'd you know to raise it to what you wanted?
Because they're selling 200 units. For each unit, the probability that it's good is 999 out of 1,000. And that's 200 times. For each unit, that's the probability. Because you sold 200 units. All right, your assignment is on page 707. 30 to 52 even.